Welcome back to the video. In this video, we'll be going through some questions from 2019 on radioactivity. So we'll be going through those questions and I want you to try those out yourself. So we're going to be going through those questions and you can pause the video, do them yourself, and then I'll explain the answers as well. Okay, the first question. A student determined the count rate near a radioactive source. She used americium source, which is an alpha emitter. She connected a detector to a counter. Now it says explain why the detector must be positioned a small and fixed distance from the source. So what we have here is this is my source and this is my, let's say, detector. So this is my source and it's at a distance D. Source, and this is my detector. Now remember, this distance must be small. The reason is if the distance between my source and detector is a lot, then a lot of my alpha particles won't be able to be detected, because remember, alpha particles have small range, so they can only be detected at small distances, right? So that's one of the major reasons why we need this distance to be small, okay? And the reason actually comes from their ionizing power. They have a lot of ionizing ability, the highest one. And because of that, they lose their kinetic energy very quickly. Okay, so that's the first thing. So you get 1 point for this. The second thing important you have to understand is that if I change this distance, then my count rate will change. Okay, so my count of alpha particles from, or I can write the counts from the source is dependent on the distance. So if I change the distance, my counts from the source that we have will change. So if I increase the distance, my detector will detect a different count, so that distance has to be fixed. So I get a fixed count and the accurate count as well. Okay, and we count rate here. Okay, so that's the answer. You get second point for this. Okay, so I hope you understand what's going on. Okay, so we have to explain two of these things: small and why it must be fixed distance. Now let's move on to the next part. Now the next part says the student measures the count for 2 minutes and divides this by 120 to determine the count rate. Now we have to explain two modifications to the student's method to improve her count rate. So let's discuss about this. Okay, now the two modifications, the first one is actually very common, and that is to consider the background count rate. So this is a very important word, background count rate. So there is this background count rate, and then you have to say what we have to do. We have to subtract the background count rate, and we're going to get our corrected count rate, and that's one of the modifications, and that's, I think, many people get that right. So that's going to be 2 marks right there. Then the second point is a little difficult to understand. It says the random nature of decay produces uncertainty in measurement. So that's going to be your third point. But what does that mean? Now we have to understand one thing. Radioactive decay is a random process. It means that it is impossible to predict when a nucleus will decay. Okay, but we know that each nucleus has a constant probability of decay per unit time, which is also the lambda. You remember the decay constant? That this is what the decay constant tells us. The probability of decay of a nucleus is constant regardless of how long it has existed for. Okay, that's one thing. The second thing, it is impossible to predict when an individual nucleus will decay as well. And another thing that comes with the random nature is that if you have a graph, okay, and you're checking the decays, you're going to have, let's say, 129 counts, 200 counts, 210 counts. So there's going to be this fluctuation. Okay, So that produces uncertainty in our measurement because the value is fluctuating. Now, this is what the point means. The random nature of decay produces uncertainty. Now, if you want me to summarize, the first thing random nature does is it makes impossible to predict when a nucleus will decay. That's the first thing. Second thing, there's constant probability of decay per unit time. And the third thing is there will be statistical fluctuations, which means you will have counts going from 190, then 200, then 190, so it will fluctuate. So 3 key points that come up in exam a lot that you have to understand. And the point they have highlighted here is that we'll have uncertainty in our measurement due to fluctuation of the count. So to decrease this uncertainty, we can increase the time for the measurement, and that will help us to get a more accurate value. Okay, so that's the other 2 marks that you're going to get. So this is going to give you 4 marks. Okay, so keep that in mind. Many students, they lost mark on this third point. Okay, now we're going to be looking at is some questions from June 2019, Unit 5. So let's go through them. Now, the first question says, scientists are still working to develop a practical nuclear fusion reactor. Which of the following explains why the controlled nuclear fusion on Earth is difficult to achieve? So the reason is that we cannot have nuclear fusion on Earth is not because we cannot have strong magnetic fields. We can create really a lot of magnetic fields, and we can get sufficient hydrogen as well. There's a lot of hydrogen we already use. We can just get more of it. And not also high pressure. The main thing that really is the downfall for us not being able to get nuclear fusion on Earth is because of high temperature. So that's going to be A. So just remember this point. It's very important. High temperature is very difficult to achieve, and that's the main ingredient to having nuclear fusion. Okay, next question. When exposed to ionizing radiation, photographic film darkens. The darkness of the film shows how much ionizing radiation the film has been exposed to. Now we have a source which is emitting alpha, beta, and gamma radiation, and it was placed a small distance from the photographic film. And we have X, Y, and Z on the film, and we can see a pattern here. Now, the darkest one means that there's going to be a lot of ionizing radiation. So this has to be alpha, and this probably is beta. Okay. Now it shows us another one, which is a second film is covered by strips of card and aluminium. Now let me just write this down here. Remember, alpha particles are blocked by paper, very thin paper. Okay. And then your beta particles are blocked by aluminium. And then your gamma will actually pass through everything, but it can get the gamma will be reduced by the lead. Okay, few centimeter thick lead, it will be reduced. It has an infinite penetrating ability, so it will always pass through, but you can reduce the radiation of gamma. Now what's going to happen is that alpha is definitely not going to go through this and this. Alpha will maybe go through this layer here, and then so this should be very dark. Okay, it should be dark, and we can see that all of them are dark around this area. Let's see something else. Now, alpha will not pass through this or this. So A and B should be wrong because it cannot go through aluminium and card. And then we have C and D, which makes sense. Okay, considerable options. And we can see that we know that aluminium will completely block all the beta. So beta will be blocked and alpha. So this should have the kind of white color. It should have a white color. Kind of a bit white because we have gamma and it has no ionizing ability because no charge. And then card will allow the beta to pass through. So this should be a little dark. And we can see that this is here bright and this is a little dark here, which is what we're looking for. And then here we have dark, which we're not looking for that because this would mean that beta is passing through. But we know beta will be blocked by aluminium, so it should be C. So C is your answer. So remember, to understand these three things, very important that you understand the penetrating ability and ionizing ability of alpha, beta, and gamma. Okay, next we have is, let me just move this up. The graph shows how the binding energy per nucleon varies with nucleon number for various isotopes. So explain the significance of the position of iron 56. So iron 56 is at the top, so it has the highest binding energy per nucleon, and that means that it has the most stability. So highest binding energy per nucleon gives you 1 mark, and the second mark is that it is most stable. So this is something simple. Let's move on to the next part. Now, next part, BC. The isotope uranium-235 undergoes fission into less, that's a key part, less massive isotopes. Okay? Now, it says explain how the fission of uranium-235 leads to release of energy. Now, what I'm going to explain next is applicable for both nuclear fission and fusion. Now, remember, the reactants, so in both of these processes, fission and fusion, the reactants will always have more mass and the products will always have less mass. Now, that would mean the mass of the system is decreasing. If the mass of the system is decreasing, right, that means that mass that goes down is released as energy. So mass decreases, and by mass energy conservation, we know that mass that goes down will be released as energy. So that's actually going to give you 2 marks to explain this. So this is a very important point for nuclear fission and fusion, both. So if they ever ask you about both of them, you're just going to write this down. Okay, next we have to show that the binding energy per nucleon of iron is about 9 mega electron volts. So first thing you're going to do is we're going to find the number of protons and neutrons. So that's going to be 26 protons and 30 neutrons. And then I'm going to do is E is equals to mc squared. So I'm going to have the mass. So the mass of the protons times the number of protons plus the mass of the neutrons times the number of neutrons. Now bracket all of that, and you're going to do times the speed of light square. So that's going to give you 7.902 times 10 to the power of 11 joules. Then we're going to divide it by 1.6 times 10 to the power of minus 13, and that will give you 493.87 mega electron volts. And then to find the binding energy per nucleon, I'm going to divide this by 56. And my final answer is going to be 8.8 mega electron volts, which is also approximately 9 mega electron volts. Okay, next question. Deduce a value for the binding energy per nucleon of hydrogen-2 from your value. So we have to use the value above to get the value of hydrogen-2, which is right over here. So this is right here. It is 8.8. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So all the way 9 down. So we can say that the value will be, the value that we had above, so 8.8 divided by 8. So basically, or divide by 9 actually, 9. Right? So it will just be, you divided by 9 to get to here. So we're going to get the answer as 0.98 mega electron volts. Okay. Alright, that's pretty much it for the question. So yeah.